So now moving to infrared. Ethanol can be produced from chlorethane in nucleophilic substitution using aqueous sodium hydroxide. Use the infrared absorption frequencies given in the data sheet, well there we are, taken from the data sheet, to explain how you could check spectroscopically the reaction that converted all the chloroethane into ethanol. Well, there's chloroethane and there's ethanol. Obviously the C2H5 bit doesn't change at all, so we're looking at the bits that do change. So we got carbon chlorine in the reactants. That should disappear as it all reacts, and as we make it, we should start to see not just a carbon oxygen peak, but also the very diagnostic, very broad OH peak for the alcohol. Okay, in practical terms, yes, the chlorine, the CCl, you can see it on a simple molecule like this. You should be able to see it going away, so to speak. However, there are a lot of times in which CCl can be covered up or obscured. Same thing, a little bit less, but still possible for the CO stretches, but this broad OH peak at 3200 to 3550, very, very diagnostic of forming an alcohol. So use the data sheet, there you go, to give a difference between the infrared spectrum of the 3-hydroxypropanoic acid and the propenoic acid. So there's the 3-hydroxypropanoic acid, that's the reactant, so you should start to see things associated with this disappearing. Here's the product, things should start to appear. Well, of course, you've got the acid group in both of those, you've got carbon hydrogens in both of those. What you have in the 3-hydroxypropanoic acid that you don't have in this is that nice broad OH peak, very, very diagnostic. Of course, the trouble is you also have an OH associated with the COOH. Now, the COOH acid is a little bit lower wave number and rather disgusting and asymmetric. This broad OH is usually a nice, beautiful, smooth hump. So you can probably see this disappearing without it being obscured by the acid. Now, of course, in the product, what you got in the product that you don't have in the reactant is the carbon-carbon double bond, which should start to appear. Again, that's kind of close to the very strong carbonyl peak that you'll see from the acid group, the C double bond O peak that you'll see. You'll hope that it will be a slightly lower wave numbers than this, that the C double bond C will be at slightly lower wave numbers, so it's not fully shielded. But anyway, pragmatically, not the best of questions, but that's what they're looking for, the disappearance of the OH and the appearance of the carbon-carbon double bond. Obscuring interesting bits can also occur in this problem. We're going from the phenylmethanone oxine, that's this one, rearranging to the N-phenyl benzamide here. You can see that it's just a rearrangement. You've got two C6H5 groups. You've got a C, an N, an O, and an H, a C, an N, an O, and an H. So there are our two structures. We've got an OH in the phenylmethanone oxime. We'll henceforth just call this an oxime there. And of course that will start to disappear once that rearrangement is happening. Nice broad peak at 3200 to 3500. And then you have this NH peak at 33 to 3500. And again, there could be a little bit of obscuring going on there between the OH and this. Now, if you had a pure spectrum of this and a pure spectrum of this, you could compare them, but you will get some overlap. What will not really overlap is this very, very dominant C double bond O, the strong peak 1650 to 1750. There will be a certain carbon nitrogen peak in there, sort of around the same type area, a little bit lower down, but it'll be much weaker. This peak will, you just can't miss that carbonyl peak when it starts to form.